We've computed the uncertainty in our parameter estimates. Well, let's work an example just to show how it works. We'll do the example of linear regression. In that case, there are only two trial vectors, the constant vector and the time vector. Well, the dot product of the constant vector with itself is just the sum over all observation times of 1, which is the number of data points, n. So the 1, 1 component of the S matrix is n. We're going to offset the times, if needed, by a constant, so in order to make the average time value equal to 0. But the average time is the sum of the times divided by how many there are, which happens to equal the inner product of the unit vector with the time vector divided by n. If we're insisting that that is equal to 0, that means that the inner product of the unit vector with the time vector is equal to 0. But that's the 1, 2 component of the S matrix, so S sub 1, 2 is equal to 0. The S matrix is symmetric, so the 2, 1 component is also equal to 0. How about the 2, 2 component? Let's deal with a special case in which the times are evenly sampled. If the average time is 0 and the time spacing between consecutive values is tau, the same constant in every case, then the times are given by this formula. We can directly compute the inner product of the time vector with itself. It's this expression, and we can work it out algebraically. I've done so to give this expression right here. We now know the complete S matrix, and here it is. Here's an equivalent form where I simply factored n out of the matrix. The inverse of this matrix is easy to compute because it's a diagonal matrix, and it looks like this. Now we're prepared to find the variance-covariance matrix of the parameter estimates themselves. If the noise variance is sigma squared, then the variance-covariance of the parameter estimates is sigma squared times the inverse S matrix, which is this. Notice that the 1, 1 component gives the variance of the first parameter, the intercept, and that's this. The 2, 2 component gives the variance of the second parameter, which is the slope. So this is the variance of the estimated intercept. This is the variance of the estimated slope. Notice also that the 1, 2, and 2, 1 components of the S matrix are 0. The inverse S matrix. The inverse S matrix is a diagonal matrix. So the covariance between beta hat 1 and beta hat 2, the estimated intercept and the estimated slope, is 0. That means that the variance of one coefficient, the intercept, doesn't mix with or interfere with the variance of the other parameter, the slope. And that's a very nice consequence of setting the average time to 0. It's ultimately because by setting the average time to 0, we're using an orthogonal basis for our model space. In other words, the trial vectors that we use to span it are orthogonal because when we ensure that the average time is 0, we know that the inner product of the unit vector and the time vector is equal to 0. By the way, if we know the uncertainties of the model parameters, we can actually compute the uncertainties of the trial of the model. The trial vectors come from trial functions. The model vector is the model without the noise. We can define a model function as the model for any time, not just the observed times, by using the estimated parameters times the trial functions. Then we can compute the uncertainty of an estimated value at any arbitrary time, whether it's one of the observed times or not, by this expression. It's the variance of the noise times the inverse S matrix times this product of trial functions, not trial vectors. By the way, for linear regression, even time spacing tau, an average time equal to 0, that gives us this quantity. The uncertainty in an estimated value of the model function or the trend at an arbitrary time is equal to the variance of the intercept plus this term, which accounts for variance of the slope. When we have, just a few data values which are generated as a true straight line plus random noise, so that the actual signal is a true straight line plus random noise. If we estimate what that straight line is by linear regression, we get the solid red line. If I take the uncertainty in the value at any particular time and add or subtract 2 times the standard deviation to get something like a 95% confidence envelope, that will be the dashed lines. By the way, there are a couple of values that stray outside the dashed lines. That's because the error envelope indicated by the dashed lines is the probable error of the model or the trend, not of the actual data. This error envelope includes uncertainty in the trend, but not uncertainty in the noise. So the noise can easily make data values go outside our error estimate, our error envelope. By the way, if I were to graph as a solid black line what the actual true signal is by which these data were derived, we would see that our estimate is quite good. Our estimated trend, shown by the solid red line, is very close to the true trend shown by the solid black line. And in fact, the error envelope shown by the dashed red lines, the error envelope for the trend itself, includes the trend at all times. That won't always be the case. The error envelope on the trend is something like a 95% confidence range at any one moment. We have a lot of moments of time, so there are many chances to go outside a 95% confidence interval. So don't be surprised if the error envelope for the trend sometimes strays outside the actual true trend.